Hello everyone, I'm Yanjun Wang. Today I'll be introducing our paper on reasoning about recursive tree traversals. This is a joint work with my advisor Xiaokang Qiu from Purdue University and Jingwei Liu and Daling Zhang from Beijing Jiaotong University. Tree traversal is a common way to manipulate tree data structures in many applications. Due to dependence reasons, a lot of applications traverse a tree data structure multiple times by different traversals. For example, the abstract syntax trees used in compilers may be traversed several times to perform optimizations. For render trees in web browsers, multiple traversals traverse the tree to compute the layout such as height, size, positions of the visible elements, and then render the pixels to screen. KD trees used in scientific simulations is another example. Tree traversals are often written as individual traversals. For performance and locality concerns, many transformation techniques are used in tree traversals. For example, running these traversals in parallel or fuse them into one traversal so that the tree only needs to be traversed once to perform all the computations. However, not all the transformations are valid. It's desirable to reason about tree traversals and dependencies between them so that we only allow transformations that tweak the order of computations in programs with no dependence violated. For that reason, there has been efforts working on reasoning about the validity of traversal transformations. Existing works such as Tree Fuser has already verified this example. However, let's consider another pair of traversals which involve mutual recursion. Odd and even count the number of nodes at the odd and even layers of the tree, respectively. They recursively call each other, and the main function runs odd and even sequentially. Even this simple mutually recursive tree traversal is already beyond the scope of all existing approaches. To generally represent tree traversals like these ones, and reason about validity of subtle transformations automatically, we propose a general framework called retreat, which allows us to reason about traversals and transformations that are not possible before. In retreat, a tree traversal is regarded as a sequence of iterations, each of them executing a code block on a tree node, performing some computations. We call it an iteration since it is like a loop iteration, and there are dependencies between iterations. A specific traversal may have their own set of dependencies. Violating those dependencies leads to invalid transformations. In order to reason about the dependence between iterations, the challenge is to find an appropriate representation for iterations. On one hand, we need to preserve as much information as possible to perform a fine-grained dependence analysis over the iterations. On the other hand, we also need to abstract some information in iterations so that the abstraction could be encoded into a decidable logic. We proposed a stack-based abstraction called configuration for iteration and encoded it into a decidable logic, which is the monadic second-order logic over trees. With the help of this abstraction, we could reason about transformations and traversals that are not possible before. We first designed a language, also called Retreat, for tree traversals. Retreat is a minimalist language for tree traversals and is designed to be served as an intermediate language for analysis. Among other restrictions, Retreat does not support loops or tree-shaped reconstructions, though these features and constructs usually can be translated into Retreat. In Retreat, user can flexibly write tree traversals in a recursive fashion. It's allowed to read or write to the local node, recursively visit the subtrees, write mutually recursive calls. Each traversal can take one location parameter and many integer parameters. Retreat also allows arbitrary statement level parallelism. Now let's see an example. The odd and even traversals we've mentioned before can be written in retreats like this, like what I have said before, the execution of a tree traversal can be regarded as a sequence of iterations, each running a straight line of non-call statements on a node in the tree. For example, an iteration could be running the non-call statement S3 on the node W, or running the statement S7 on node N. However, given this information, it's still quite difficult for us to distinguish the execution order of these two iterations in the program. Recall that how we figure out the execution order of iterations by manual inspection. We could use call stacks. When these two iterations are running, their call stacks look like this. The last record on the stack shows the code block that is running currently, and all the other records are the call contexts. Each record consists of a callee block, the value of a location variable, and the values of some integer variables. By inspecting these call stacks, we can determine the order of these two iterations. By pairwisely comparing these two call stacks, we could see that these two iterations agree on the first several records in the call stack and diverge on the fourth record. We have noticed that when two blocks belong to the same function, there are only three possible relations between them. They could be sequential, for example, S1 and S3 in the function odd. Or they could be conditional, for example, S0 and S1 in function odd. They are in different branches of the if statement. Or they can be even in parallel. Since S1 and S2 are sequentials in function odd, we can conclude that the iterations shown by the call stack on the left execute before the one on the right. However, not every random call stack represents a valid iteration. Let's consider a program that is slightly different from the one we have shown before. Here, the function called even is invoked conditionally on the return value of odd, which stores in the field n.odd. Given a call stack like this, a set of pass conditions is needed to be satisfied for the call stack to be a valid one. For example, S8 is the first record in the first record should be less than 5, so that there could exist the second record in the stack, which means S9 is invoked. Also, node U should be the right child of root R in the tree, since the record shows that a function called S6, which is a call to the right child, is running on node U. These kind of pass conditions can be mixed with sophisticated arithmetic constraints. It is not too hard to prove that even determining if a call stack is a valid stack is undecidable. As precise reasoning about iterations is undecidable, we proposed an iteration representation, which is called configuration. The idea is to abstract the recursive calls, ignore the return values, and use ghost variables to predict return values in the call stack. The other part of the configuration stays the same as the call stack. If the pass condition with ghost variables can be evaluated to true, we assume that the iteration is speculatively reachable. In this case, S9 is speculatively reachable. Due to the speculative execution, pass conditions are more easily satisfiable. Take this partial program, for example. Function height and size recursively compute the height and size of the tree. F of n.l will be invoked under the case that h is equal to 5 and s is equal to 3. Since arbitrary h and s values are legal due to speculative execution, the call to f of n.l is considered reachable. However, f of n.l is indeed unreachable during real computation, since height of a tree can never be greater than the size of the tree. The precision lost results in incompleteness of this retreat framework. After defining the configuration-based abstraction, we're ready to encode the schedules and dependencies between configurations into monadic second-order logic over trees, which can be solved by the state-of-the-art solver Mona efficiently. Configuration can be represented as a tree with labels. For example, this configuration can be represented by a tree with this set of labels. We introduce the label for every record for every code block in the program. Each label is a set variable in monadic second-order logic. The label LS6 is marked on node U, means that there exists a record S6U ... in the configuration. Now we can encode configuration to monadic second-order logic. We define a predicate called configuration, which means that the set of labels represents a valid configuration that is running some non-code block Q on node B. The first line claims that the label for main function is marked on the root. The second line enforces that Q is the only non-code block marked on the tree. The third line says that every record except the last one has a unique successor that can reach 2. The next here is a subformula ensures that if there is a record SU ... in configuration, then the next record is of the form T ... The fourth line constrains that every record has a unique predecessor that can reach from. Proof here is also a subformula ensures that if there is a record TU ... in configuration, then the previous record is of the form S ... The last line makes sure that the past conditions are satisfied for every record. Now we know whether a tree represents a configuration. Given two configurations, we also need to know whether they can occur in the same program execution. We call this consistency between two configurations. If two configurations are consistent, they should agree on the shared part. Given two configurations, there should exist a node Z where these two configurations agree on all the records prior to the diversion node Z. The next records after the diversion one can be reached at the same time. Defining consistent allows us to encode schedule relations between two configurations. There are two possible relations between two configurations, ordered and parallel. Predicate ordered enforces that configuration 1 precedes configuration 2, and predicate parallel indicates that the order of configuration 1 and 2 cannot be determined. Given two configurations, if the records of these two configurations diverge on a node running code block S, and the next record in configuration 1 is T1, and the next record in configuration 2 is T2. If T1 precedes T2, then configuration 1 should precede configuration 2. If the order of T1 and T2 are not determined in the program, then the order of configurations 1 and 2 are also not determined. We also encode the dependence between two configurations into a monadic second-order logic formula. Dependence exists between two configurations if these two configurations are valid and they access the same field of the same node and at least one of these accesses is a write. With schedules and dependencies defined, we can encode some dependence analysis queries related to traversal transformations to monadic second-order logic over trees. For traversal parallelization, we could check if there exists data dependence between two parallel configurations. Besides data race detection, another critical query is the equivalence between the original program and the transformed program. Since the common transformation, such as fusion or parallelization, only reorder the operations of a program without modifying the code in code blocks. The equivalence checking problem can be reduced to the problem which compares programs that are built on the same set of straight line blocks and there exists a mapping between these two programs. With a given mapping, to guarantee the equivalence of original program P and transformed program P prime, it is sufficient to make sure that the transformed program P prime does not swap any pair of ordered configurations in the corresponding original program P with data dependence. We have prototyped the retreat framework, which leveraged Mona, a state-of-the-art monadic second-order logic solver, as our backend constraint solver. We have evaluated retreat on 4 case studies. Our first case study is the running example presented. Retreat is able to verify the feasibility of the mutual recursive calls of odd and even. And we also designed an invalid fused traversal and encode the feasibility to monadic second logic over trees. Retreat returned a counterexample that illustrates how the data dependence is violated. Since retreat is sound but incomplete due to the abstraction, we manually inspected the counterexample and verified that it is a true positive. We also used retreat to verify the data rate's fairness of running odd and even in parallel. Cascading style sheets are a widely used style sheet language for web pages. In order to lessen the page loading time, many minification techniques are adapted to reduce the size of CSS documents so that the time spent on delivering CSS documents can be reduced. The abstract syntax trees of CSS code are often traversed multiple times to perform different kinds of minifications, such as shortening identifiers, reducing white space. It's desirable to fuse these traversals to enhance the performance of this minification process. In this case study, we considered 3 minification traversals and verified the feasibility of them. Notice that these programs involve conditions on string which are not supported by retreat. When being written in retreat, these conditions are replaced by some arithmetic conditions. Cycle trees is a well-known network topology in the network community. It is a special class of binary trees with an additional set of edges and has been proved to be very efficient. In this case study, we considered 2 traversals regarding cycle trees. A traversal called root mode is a mutually recursive traversal that constructs the cyclic order on a binary tree to transform the binary tree to a cycle tree. Another traversal, compute routing, computes the router data on each node, which are essential for an efficient cycle tree routing algorithm. Retreat can verify the feasibility of these 2 traversals and return the counterexample when checking the data rate's fairness of these 2 traversals. We manually inspect the counterexamples and verified it is a true positive. In the last case study, we consider this pair of list traversing traversals, sum and shift. Traversal sum updates the local field B in the list to the aggregation of values B in the list. Traversal shift shifts the element in the list to the left and sets the last element in the list to be 0. A program invokes sum followed by shift. These 2 traversals can be fused at the cost of introducing an extra field to store the intermediate results in each node. However, if one swaps the order of these 2 traversals, they can be fused without introducing an extra field. Retreat can verify the feasibility of the swapped traversals. However, since there does not exist a relation between the original and the swapped traversals that preserves all data dependencies in the original program, Retreat cannot verify the validity of the swapping process. We used SRT, which is another MSO-based technique, to verify the swapping step, and then used Retreat to verify the fusion step so that the whole chain of optimizations can be verified. In summary, we proposed a framework called Retreat, in which user can flexibly write general tree traversals. We developed a stack-based, fine-grained representation of iterations near tree traversal. Based on this abstraction, we presented an MSO encoding that can check data race freeness and transformation correctness automatically. Our approach is more general than existing techniques and allows us to efficiently reason about sophisticated traversals and subtle transformations. Thank you for your attention.